Okay, so let's see. I I guess I got lots of frustration last time, most likely, and so I guess my problem was that I thought you guys had background on signal and systems, which is actually a core course in EE. So I think I didn't know like what I put as a prerequisite, but in any case, um, I guess what I'm trying to do now, or actually maybe I say one more thing is uh yeah, I think this is of course it's not the first time I teach this. Like most likely like there were students I also had this problem, but I was not realized that because like typical students are really good at like putting up their poker face, and actually it's harder, even harder to get feedback like when it's teaching like kind of face to face lecture. So therefore, like this kind of feedback, like it's really great. So for the participation and and the so-called quiz here. So for one thing, like please don't be too concerned or worried if you are not able to answer all the questions, because by design, like we don't want to have the questions are too easy, so that like you will either get bored or like uh you probably will get like actually, in some cases, you probably will have like enough points to pass the A threshold even before you submit the final project. That happened before, but we definitely don't want to have like majority of the class will be like that. So but in any case, what I plan to do so therefore is let me just give a very what I want to do is I'll squeeze a one semester course of like signals and systems into 30 minutes. So and of course I will omit lots of stuff. So for those of you who are familiar with this kind of materials, kind of like please bear with us. I will just hopefully take like half an hour or so. Um, of course, I because of that, I'm going to omit lots of, I mean, rigorous detail, but like pretty much high level and layman explanation. But I have put some. I sent you guys email uh, on a book like there's a classic book on like signals and systems. I don't think you need all these materials for this class, but for this class and last class and the next class, it's good that you have like some background on signals and systems. So therefore, like I decided to just give a kind of really brief and short introduction. So but before continue, let's get back to where we stuck. I just want to make sure that like we are all on the same page. So let's say we have remember like last time we have this decomposable filter, and we are trying to trying to we just say like this is decomposable like into like two different filters, or like you can think of like it's because this matrix is a can be uh, written as a multiple of like product of like these two matrix, or like these two vectors, like column vectors and with row vectors. So now if we apply a filter to an image patch, it's basically just a pull out a patch here. Like for example, if I consider like at this point here, I want to find the filter value at this point, I'm basically just take out this patch here of this image and do a dot product with the filter. So if you are not familiar with dot product, it just means that like, I have element wise product like for each of these element, I will kind of like multiply them together and then sum them together. So therefore, in this case, if I have an element-wise product of this patch with the filter, what do I get? I get like 1, 2, 1, 0, 0, 0, minus 1, minus 2, minus 1 back again. Now I sum all the elements together of this product, we'll be just getting 0, right? So therefore, the first value is 0. Note that in this case, I I do not do any padding, so therefore like I cannot compute, let's say value here because I don't have neighborhood pixel, neighborhood values for this pixel here. So therefore, you see, like I have this dimension of this image shrink by from 5 by 5 to like this 3 by 3 here. So, but um, of course, in practice you can do some padding. For example, like I can do some padding to get back 5 by 5. I can just pass zeros outside that. That uh, that is just some minor detail. So now I can do the same thing. For example, I take this pixel here. What do I do? Like I take this patch here, and then I do a product with the filter, right? So element-wise product, I will get like 1, 2, 1. Now this time it's 0, 0, 0, and it's 0, 0, 0, right? Because this 0, 0, 0 multiplied by -1, -2, -1 will get back just 3 zeros. And then if I sum them together, I get 4, right? So therefore I have value 4 here. So, and then if what I what just mentioned that like this filter is decomposable, I can get it. It's a row vector, sorry, a column vector and then row vector. So I can apply this filter like first vertically and then horizontally. So let's say like if I apply vertically, what then I take, let me, well, this is a bit messy. Let me just get all this out of there. So vertically, so for example, like then for this one, for this pixel, then I will just take this row here, right? And then I take a product with this filter. Now it's just F1 here. We'll get like 1, 0, -1, right? And I add them together, I get 0. And then if I take the next one, let's say this one here, take this one, then I take the neighborhood, it's like this guy here, then multiply with this one, I will get like 1, 0, 0. So therefore, like add them together, I get 1 here. Yeah. So after I do the vertical filtering, I can do it horizontally. So with like F2. So if I do F2 on this guy, so you can verify that like it will just get back 0, 0, 0, 4, 4, 4. So it's the same things as this one here. So it's basically the same. So you can verify also that I can do it like first horizontally and vertically, it will get me the same thing. So we gave a proof last time, like rigorous proof for that. So I won't repeat that. But if you have a decomposable filter, you can do it like horizontally and vertically. So okay, just make sure that like you guys are following at the same page. Let me just like have another image and I apply on the same filter. If let's say if I have an image 1, 2, 2, 1, 1, 2, 2, 1, 1, 2, 2, 1. So if I'm going to apply this filter F on this image, so this F on this image, so F. So what do I get? So this is a question. So just want to make sure you guys are at the same page. Oh, be very careful, no padding. F. Yeah, apply F, not F1. Yeah. So note that like I'm applying F, not F1 here. Yeah. If I apply F to this one here. Okay, I see that most of you have answer, I guess. No, actually, there's still like several more coming up. So uh, I guess like more or less all of you answer probably. So uh know that like it's just okay. Some of you answer correctly, but I guess still like quite a lot of you like answered like not correctly. So you we are applying on F. Know that without padding, like this one I cannot compute any value for that because like this filter size is this one, right? I don't know what's this value here. So therefore, like I cannot compute the filter value for this patch here. So the first pixel I can compute here is only this one, right? So I can take a patch, like the neighborhood patch would be this guy here, right? And then I can compute anonymized product, then I will get like 1 2 1. Sorry, like not 1 2 1 in this case. 1 4 2 0 0 0 -1 -4 -2. Then if I sum of all of them together, I get 0. So therefore, 0, this one is 0, that's 0. Then I can do it again like for this one here, and I will also get 0 basically, right? But I cannot get like anything outside that, yeah. So therefore, like it should be just 0 0, yeah, when there's no padding. So okay, so I hope like this is clear now. So everything is clear like this. So now I will give a really try my best to squeeze like third, I mean a semester of like signals and processing into like 30 minutes. So I just prepare like some white up here. I mean I guess it's easier to just let's see. So okay, like what signal and system do is like basically like okay, it just sound like okay fancy, but like you just have signal, right? You have signal, and then you have system. System is just anything that going to process the signal. Then the signal typically will input into the system and then output out of the system. Then that's it basically signals and system. But the key point is like okay, your signal can be like different, can be 1D, 2D, high dimension. Typically, people start with like 1D, right? 1D can be like a 1D signal, maybe just like the stock market price. Maybe I just want to look at just the last stack, the stock daily price. Yes. So and then like I have of course like 2D signal can be image, right? And image is a 2D signal, and then I can video can be considered as a 3D signals. I go to into 3 dimensions. So okay, let's start with like 1D signal first. I have 1D signals here. So the most important kind of like core topics like in signals and system is like the frequency and also frequency interpretation. Okay, let me get a poll here. Like I want to get some feedback. How many of you have background on Fourier transform from any class, either math or like engineering? Okay, that's great. So this will be more or less like a revision here. So Fourier transform is nothing. It's just trying to get a signal from the original domain. So typically, the original domain will call it either time domain or spatial domain because we say time because like when people first study like one-dimensional signals, it's always just time signals, right? So like we have like for example daily talk stock price or daily last stack like index, I mean value like will be just each day like for different day, like today, yesterday. So the x-axis will be time. But of course, you can also like analyze that in terms of spatial like signals. For example, if you have two-dimensional signals that like image, then the axis here will be like the space, right? So I have like x-axis in one, I mean, horizontal and y-axis vertically, let's say. Now then, as I said, like okay, back to Fourier transform. Fourier transform just like trying to convert from like the original domain into like so-called frequency domain. So what does that mean is that the main theorem of like Fourier, like discovery of Fourier, is that actually it's quite interesting. Like before Fourier, like actually at the time of Fourier, like proposed this, many great scientists thought he's crazy, like include Laplace. Laplace is like this really, I shouldn't say lasty guy, like a genius, but he's really cocky and like to say nothing I cannot predict and so on and so forth. And he thinks like this is like I don't know pseudoscience. Like when we first like introduced this, and basically the idea is quite simple, but maybe revolutionary like at that time. So it's that like you consider any signal, it can be interpreted or like it can be decomposed as like sum of sinusoidal alternating signal. Sinusoidal, I mean alternating, like this one here. So I just put in one example here. I have a step function, right? I have step function, and then like I can actually decompose this step function into lots of like sinusoidal signal, like or like alternating signal here. So I split into like different components. Like this is like the first component will be having like a DC component. So basically not alternating, just a constant signal. So you see like here is not 0, here is 0.5. This one can be decomposed as I first having a 0.5 here. It does make sense, right? Now then if I add also like an alternating like frequency of 1, frequency 1, I mean that like uh for the entire length of the signal, that will be one cycle. It's just oscillating one time. So I have one cycle here. I add this guy together, I get this one, right? So it's a little bit more better approximate than the original constant signal here, right? So if I want to approximate this guy after I adding this, so now I get an oscillating one like this one here. It's a little bit better approximate. Okay, I'm not trying to draw it, I just like getting more and more, but it's showing here. So now I can add one more. Actually, the third one will be getting, I see, like one cycle, two cycle. So two cycle, it doesn't actually, it turns out like it doesn't have a component for this test function. It doesn't have a component of two cycles. So therefore, like that's basically just 0 here. So I have nothing here. Actually, it's easy to argue why you don't have like two cycles, but because like you see this signal here is like is if you have like a two cycle here, the two cycle signal is symmetric at the middle, right? But this signal, this step function is exactly anti-symmetric, so therefore like it won't contain this one here. So, but I can continue to do that. Like so, it's also like let's say like it contain also like uh signal of three cycles. And note that like for this axis here, like uh the value is not the same. Like this cycles is like this one, the maximum value is maximum magnitude is about 0.6, let's say. And here the maximum magnitude is only 0.2. And I can continue to do that. Like so if I have like these four added together, or sorry, like these four, I should say. So these four components added together, now they get more similar, more closer to the step function now, right? I can continue to add more components. So it's getting more like and more like a step function. So the point is like you actually can decompose any signal, and you want like in this case, like any 1D signal will be like just some of like alternating signals. And then like, so what is Fourier transform is like, So you see, like I have like different magnitude here, right? So Fourier transform is basically it store like the coefficient of like what's the weight. I have like weighted sum of this sinusoidal signal, right? Fourier transform just store the weights basically. So if you look at the frequency representation, so this is a frequency representation of this original step function. And I will have like quite a lot of DC component here, as you can see. And for the next, let's see, for the next frequency, I will have a little bit of that, but it's not clear. Maybe like around here, I have some like at frequency one, that's basically one cycle per the entire signal that have so much energy, or like the weight will be so much. And the next one, I will have zero, right? Just like here. I have no component with like frequency equal to 2. Then I have like a little bit of frequency of 3 is like here, right? And then again, I get nothing like for frequency of 4, and so on and so forth. And also know that like for the frequency here, of course, without going to math, I cannot prove that. Frequency go with pair in the sense like the negative frequency is the same as positive frequency. Another remark is like your here the Fourier transform is actually complex. So the values is complex. Of course, you have taken Fourier transform before. Maybe I will give a more mathematical revision next time when we actually will talk a little bit more Fourier transform. But here, like just know that this is complex. So what I'm showing here is actually just the magnitude of the signal. So let's see, anything I miss here? So then okay, what I'm showing here basically, if you look at this here, I'm just showing take this, okay, the DC component, I'm showing the DC component, and this one I'm showing that for frequency one, the of this uh frequency representation. Basically I take everything to be zero except like frequency one, and this one I take everything to be zero except frequency two. But of course, for the step function here, frequency two has nothing here, and then I take frequency three, frequency four, and so on, then add them together. So is that clear? Like Fourier transform, and then of course, you can do Fourier transform in 2 dimension as well. So if you take 2 dimension, then you will just like go in 1 dimension, like maybe first I do it horizontally and then do it vertically. But we'll talk more about that like next time. So for 2 dimensional Fourier transform. But then like let's go back to like maybe like some of this confusion last time. So we
Dr. Chang, I have
yes,
a question.
yes,
Can I ask a question?
yes, sure.
Okay, so I have a question about, for example, the frequency one.
Yes,
So if you look at that, so
yes,
it looks like just a sine function, right? In
yes,
the spatial
yes,
representation.
yes.
So y frequency is like a +1 and -1?
You mean here +1 and -1?
Yes.
Yeah, yes. Okay, that part I guess I will elaborate next time. But uh,
Okay.
I guess the frequency that's if you remember. Okay, maybe I can just like doing ahead like actually the Fourier transform. Okay, for guys like you don't I don't know. I mean, if you don't worry about the math right now. I just want to quickly answer his question. So actually, what we did in Fourier transform is that you have like xn, let's say, and then you sum over this n with this sinusoidal, but it's a EJ kind of like omega, like for different frequency, right? It does have a physical meaning. Yeah, it actually has a physical meaning. So for the exact physical meaning here is like your +1 and -1 frequency is actually correspond to like one cycle uh, of the signal here, like per the entire length of the signal. Of course, here I'm restrict myself to finite length signal because like this is a computation class. Like we won't go have an infinite size image basically. So for finite length signal, frequency 1 is precisely like you have like oscillating one cycle, and frequency 2 will be like oscillating two cycle and so on. But you have like plus frequency and negative frequency together because like your equation, if you remember, this is actually the frequency. Like, let me just write it omega as I usually people does. Like frequencies, the omega will be like different frequency here. So your omega will be a real value, right? So omega will be this, not exactly equal to 1 to something. So actually, the omega will turns out will be something like 2 pi k over n. So n is the length of signal. So the k here will be this axis will be the k, will be the frequency. You see, like for k is positive and negative. If you remember this uh this what do you call this exponential of like this Euler thing, like exponential of this I thing. Oh, sorry, like if you're from physics, like it's exponential I something. Like in engineering, people like to use J because like I stand for current. So so then like you see like I have like omega is like plus and negative is correspond to same sinusoidal things because the exponential I multiplied by something multiplied, for example, ei omega t here is just an oscillating signal with different, when I have different omega, we'll have like different frequency. So if I have like omega equal to, instead of like omega, I have ei omega t, it will be same oscillating signal, but it's oscillating like just the sign will be reversed. So did I answer your question? Kind of like, so therefore, like for both like positive frequency and negative frequency, it's actually like the same oscillating, not same oscillating signal, but have the same um same frequency. So therefore, we need to group them together. Yeah.
Okay, thank you.
Yeah. So yeah, again, like for guys that kind of don't follow the math, like don't worry about that. We don't need this math like at this moment. Maybe next time I get more detail. Um, and actually, one remark here. Okay, maybe this making a question. Like, see, so if in this case you see my signal length is like 64, right? Actually, you cannot see, but like the length is 64. You can read it from the graph also, but let's ask it anyway. What is the highest frequency I can have? Okay, okay. Wait. Okay. Let me do it this way. I can use my handwriting is very hard to write. I have to write well with this thing. So, what is the highest frequency we can have for a signal of length 64? Let me say like frequencies like in what we discussed here. So you can define frequency as a number of cycle per the entire thing, per the entire length per entire length of the signal. I don't know, my English is not that great. Entire length of the signal. Okay, so I see like okay. I guess I more or less have like all you guys answer. So let me 64 maybe a bit long to actually you can see here the largest is like 32, yeah. Because I can that's okay. I got a hint here, like maybe like the axis yeah, if you of course you cannot read it easily, I guess. Or so, but let's see. Um uh if wait a sec. If let me take a shorter length, maybe like it's easier to explain. So let's say if my length of this signal just 8. So I can the maximum number of cycle can only be 4, I will argue, because what's the signal will be, let's say, will be just first a 1, right? The length is 8, I then have minus 1, 1, minus 1, 1, minus 1, 1, minus 1, right? Or like the other way around, or minus 1, 1, 1, 1 first, right? But then like there will be like 4 cycles here only, right? And I cannot get more than that. Right? So therefore, like if I have length, if length is L, then the number of cycles, or like maximum number of cycles I can pack for that length, that would be the largest frequency, will be just L over 2. Yeah. Yes. So okay. So I hopefully like everyone has the minimum knowledge of the uh, needed knowledge of Fourier transform. And then like, okay, one thing I guess maybe could have, I'm not sure, like could have confused you guys last time is like this high pass and low pass. So now you have this frequency representation of the signal. So we have this high pass and low pass filter, just meaning that like if I have a so-called like a filter, like okay, like filter when it first started in signal processing, it's usually referring to this kind of high pass, low pass, and band pass filters. Basically, just saying that okay, if I able to filter out like some of the frequency, let's say I have a low pass filter, it'd be like this. So basically, I will basically get everything. Okay, I didn't draw very well. So maybe like for anything like outside frequency 10, I'll just like can kind of suppress that to 0. And for anything that inside this one here, that will keep it here. So that will be a low pass filter. And then I can do the opposite. Maybe I can have this is too many stuff, right? I can have like something like that will be a high pass filter, right? So it will be like suppressing anything. So you can see like what I'm drawing here is basically drawing uh, a frequency representation of a filter. So let's say I have some filter that have a frequency representation of this shape here. Okay, I need to find some space to draw. Let's see where can I draw. Okay, okay. I guess I probably the best thing I can do is I just copy this thing to somewhere so I can, or maybe here. Maybe I just use here. So actually, I'm already showing this one here. So I have a low pass and high pass filter. I say that way. High pass will be something like this. And this high pass I'm showing here is the frequency representation of some signal. Actually, also is something interesting about like this signal processing is like uh the classic signal processing theory is like pretty nice to signal and filter. Is actually you can have this same kind of representation. You can also have the filter and can treat the filter as signal as well. What I mean is like last time, if you remember, or actually just a couple of slides before, we have a a uh, a filter of like just 2 1 1, right? Let's say, right, 2 1 1, and then I can also compute the frequency representation for that guy. So, but I let's say I have the signal length of 64. I can treat this signal actually also like uh, as a length of 64. I will just pass some. Okay, maybe I shouldn't get even that. So, but anyway, I can get the frequency representation of this guy. So let's say I can get frequency representation of this guy, and the frequency representation of this guy actually I probably have showed that somewhere. Uh, this time, yes, this is like the 1 to 1 here. This 1 to 1 here. The frequency representation actually it will be have a shape like this. And you see like it's a low pass filter, but it's not ideal. It's not like this, like very sharp, but it's like some kind of low pass filter. So again, like this, you have to take me for granted now. Again, like this is not something that I can go into detail unless I go into math. So when we do filtering, so we have a signal here, start with a signal. When I filter with this another signal, it turns out that it will be just the same as I have the at the frequency representation of the signal here. This is the frequency representation of the signal. Multiply the frequency representation of the filter. Literally just multiply. So therefore, like if I have a filter is have a shape like this, then it will basically will suppress everything outside this here, right? So for the current filter here, like for this particular filter here, even though it's not really so great in terms of like suppressing that, but it still have a low pass effect, right? So it's suppressing stuff like that's getting high frequency. So so therefore, like this multiplied by this, I will get something like this, where you have a little bit suppressing here. And if you go back to the original domain, you see that it's moved out a little bit like this. So is that clear in the sense like you do filtering in the original domain is same as doing product in the frequency domain. So and then like you will see like why is have this low pass and high pass last time. So we have this filter 1 to 1 will have a shape like that. This is a low pass. And then like I have like 1 minus 1, something like that will be high pass. Actually, I can I didn't have it here, but I have a let's see, I need to pull out my uh I need to find where is my uh oh, where is that? Okay, I guess it's here. I guess maybe I move this around first. Let's see. I have space here. Oh, okay, wait a second. I've used here. Okay, that's great. So this I always also prepare this just in case. So um so this is an example for that. Like I have a high pass filter. Let's say the high pass is I just minus 1 1. So I will claim is high pass. And if I look at the frequency representation, it's like this. Oh, okay. I need to pull the chat here, like to this. Yeah. So if frequency representation like this. So it's not suppressing everything like for low frequency, but at least like for the DC, it just says to 0, right? And it's going like this. So and I can like say like try another high pass. So my signal length is like 8 here, or actually it's like 16 here, but okay, let's keep it 16. So I can do another filter like this one last time. So one as I said, like this one, actually, one of you guys I point out is like more like band pass because I at really high frequency also like suppress that. But it has some like uh low pass, so some high pass characteristics. So usually like, people use this as a -101. Usually, actually, that's what we what that was the example like at the beginning, right? Beginning of the class. Usually it will be used as a high pass. Uh, Even though know that they also suppress the very high frequency, but for the very high frequency, it's typically okay because the very high frequency is noise usually. So it's kind of okay. So I can oops. Why I probably open in another place. So anyway, uh, so I can and let's see, go back to that one here. Note that like for where's that? Oh yeah, it's here. Sorry about that. So for high pass, like typically you have oscillating signals. I mean the coefficient of the filter will be oscillating because you think of like when you when they oscillate and you just like sum this filter together, it gets zero. It means that if you apply this filter to a constant region, then you get back zero. That's what you expected, right? Because I when it's like things is constant, then that would be like low frequency, right? So um and so therefore like what I want to point out here is also like when you have like this is like oscillating, it's typically high pass. And then if your filter is like kind of averaging, like for example, like if I have filter, uh, I guess I don't need it now here. So what I mean is that let me just repeat. So if I have like something like, for example, 1 - 1, this will be a high pass because you this is a some if you think of like you have applied this as a constant region, maybe I have 1 - 1 - 1 - 1 here. I apply in here, then I will just get zero, right? I have this part like have a dot product with this guy will be zero. And if I have like 0 - 1 also have a high pass property because I apply this to a constant region also get me zero. Uh, on the other hand, if like you have something like say 1 - 1 or 1 - 1 and so on, this would be a low pass as you apply to something is oscillating. Let's say if I have 1 - 0 uh, 1 - 1 1 - 1, if I kind of apply to here, that will give me zero, right? So therefore, for the high oscillating signal, it will going to suppress that. Same as I maybe like I have 1 - 4 - 6 - 4 - 1. Also, it's kind of low pass. So again, like okay, let's again like some thing like to check your understanding. Like so I have one uh let's see 1 - 2, 2 - 1. So is this a low pass or high pass filter? Is this low pass or high pass? Okay, most of you get it right, but some of you still didn't get it completely. So know that like very easy to verify whether it's low pass or high pass. It's just that you actually apply this to a oscillating region or an oscillating signal and like or am a constant signal. So if I apply to a constant signal like 1 - 1 - 1 - 1 - 1, something like that, if I get it to be zero, that means the low frequency component is like is wiped out, right? So therefore it should be a high pass. So if I have high pass, meaning I let the high frequency get full, right? And the low frequency just get blocked. And if I apply to an oscillating signal, and if I have the if I have that get blocked out, is getting to zero. So if this zero, so I mean like if I apply a filter for constant signal, I get zero here, I will be like a high pass, right? The low frequency is like suppressed, or like at least the low frequency is gone. If I have like an oscillating signal get into after I filter get zero, then it will be like low pass. So in this case, I can test it like on a constant signal here, right? So if I constant signal, I have this like 1111, apply filter on this one, I will get just zero, right? So therefore, like it is actually a high pass. Uh, yeah, that's fine. Yeah, so yeah, the name sometimes is confusing because they say low pass, but it's yeah, but it's set pass, like so yeah, so you get used to that the name. So it's just sometimes the name may not I mean like yeah, but it's okay. For this one, it's not exactly bad, but I there's some name is even worse. So okay, let me continue to give a little bit more introduction for signals and systems that is uh to be honest, I think if you just do a computation with like what I want to say like do an app and then I mean you open Siri and something like that, you probably don't need this. But on the other hand, like this is a background knowledge. People expect that like if you're knowledgeable in computer vision, cell processing, and so on, you should know that by heart. So I guess I would still cover that, and because I also like when you read paper, people say okay, it's linear and it's a shift invariant and so on. Like you're supposed to know that, like so therefore like I'll just like mention that. So I already like kind of like mentioned that last time. Like so one thing that is for a system uh that people like to there are of course like, we can introduce lots of properties, but there are two properties I think is most important. Like if you for the suggest textbook I mentioned, like this appeared even like in the second chapter, you see how important it is. So the two properties is a linear and shift invariant. So sometimes like people call it time invariant and so on, but I would prefer like shift invariant. I think it's a more appropriate name. So so basically, like for linear system, I mentioned that last time. It's actually a very simple concept. So let's say if I have like a signal that I can decompose into like, for example, I have this drawing here. It's like these two pieces where I have like signal like A and B. This is like A plus B here, right? So now if I apply the system or like whatever filter or think of a system more general system may not be a filter but just a system after process that I have like SA plus B here. So and if is this SA plus B turn out is just equal to SA, oops, how do I write here, it's hard, SA plus SB, then we say it's linear. So more more actually more accurately here I'm kind of like uh, more accurately you will see that like the precise definition will be like as lambda a plus let's say beta b is equal to lambda s sa plus beta lambda b. Sorry for my handwriting, it's very hard to write. Okay, I need to write slowly. Beta lambda, sorry, beta SB. Yeah, okay. So of course, if I just show here is the case when lambda and beta is equal to 1. So, but yeah, this is the actual definition, like precise definition for system to be linear. So that's for linear system. Another very important property, as I mentioned, is shift invariant. So shift invariant meaning that actually it's the meaning is just you have the operation of the system is the same like regardless where you're applying to the signal. So it's like you if you apply the system here, you're going to apply the same way here. So you're not going to like do it differently. For say, let's say I like to make the corner here using a different operation than like this lower corner here. So if like you have something like that, then the system definitely is not shift invariant. One thing like you can verify like whether a system is shift invariant is like that's why people call it shift invariant. It's like you try to um, apply the system to the signal, and then like you shift the signal. In this case, I have a translation here. I shift the signal and then I apply the system again. So if I have the signal is shift invariant, then I have the signal first shift that and then apply the system will be the same as I first process that we process the signal with the system and then translate that just like this. Like both paths will get me the same solution, same answer. So that's shift invariant. So so now why people are interested in like shift invariant and like linear. So in terms of like that's a important theorem that again we cannot go into detail for that, but you should know it by heart also. Like if you have a linear shift invariant system, then it will be just the same as filtering. Then it if you have a system like this, I have a system that is both uh, linear and also like shift invariant, then I can find some filter such that this system can be replaced by this filter. So I have this whatever signal here. I whatever this operation, I can find some filter, exist some filter, such that that system can be replaced by this filter. So then on the other hand, you can think of like where's the limitation of doing filtering, or or like if you think of like anything can be done by filtering, that means that like it should be a linear shift invariant system. And yeah, okay. So I guess that's more or less I would like to cover for uh I mean, it's a little bit more time than, but let's see. For one thing, like I want to put a catch immediately that I was actually lying a little bit. When I say filter, like what I'm showing here, I'm doing convolution. Um, and for this theorem to hold here, people are doing this. Oh, sorry, not convolution. I'm doing actually correlation. And for this one to hold that, like actually is doing convolution. But the difference of convolution and correlation is just that like when I do a when I apply a filter uh, to the signal here, when I do a correlation, I'll just like apply the filter literally. Let's say I have like filter is -1, 0, 1, and I have signal 1, 2, 1, 2, 1 here. So if I do correlation, what do I get? I will have uh, I will just like have this one uh, just do a dot product of this guy. So I will have like 0 and then have like uh 0 again, like something like this. Maybe I didn't pick a very good signal. Let's pick this. So it doesn't have like 0. So let's say I have this here, I guess I 2 0 and -2, let's say. Now if I do a convolution, this is correlation, a convolution, the difference is I need to first flip the filter. So I will flip the filter into like 1, 0, -1. and then do the same thing as before. So 1, 0, -1. So apply to this one, then I will get -2, 0, 2. So for this kind of like the core theorem, yes. Okay, let me repeat again then. The difference of correlation and convolution. Okay, 1, 0, -1 is just a flip the filter like uh, in the horizontal and vertical sorry, flip the filter um in the horizontal direction. So I get like this one start with 1, and then the second one is 0, and the third one is -1. So give another example, maybe like 1, 2, 3, 1. If I filter like that, I will get 1, 3, 2, 1. So um and then yeah, okay, maybe I just again I check you guys understand like what we are doing here. Let's say I have a filter 1, 2, 3. I do convolution. Be careful. I do convolution on 1, 1, 1, 1. This is convolution. So what do I get? This is the filter. This is F, let's say. So I have like filter with F here. So what do I get here? Okay, maybe this is a bad example. I'm sorry. Let me put like this. Okay, that's bad. If it's still bad, I'm sorry. Let me, that will give me whatever. It didn't test anything. Let me put like 1, 2, 3, 4. Let's say. So it's a little bit more difficult algebra. Yeah, like this. So what do I get? Not algebra. This is calculation. Yeah. This is a this is also a test of your primary school like no, we're doing okay. You know how to do correlation, right? When we do correlation is like okay, what we're talking so far is like just do a dot product like with that. We're doing convolution is like um we need to first flip the filter first. Oh, we're not doing correlation, convolution. Yeah. Yes. So and anyone have like yeah, let me write it. Sorry, 1, 2, -3. The filter is 1, 2, -3. Let's say 1, 2, -3. Okay, more of you like so. Okay, I guess most of you get that. So I should first flip this. So I have like -3, 2, 1. So that is a -3, 2, 1 multiplied by this will be like -3, 4, 3, and then I sum all them together 4, and then apply to the next one here is a -6, 6, 4. Again, I will guess 4. Yeah. So okay. So you're
So
following like
Dr.
what?
Chang, I have
Yes.
a question about the convolution.
Yes.
Usually standard way to calculate the convolution is from, so for example, in this case, the filter is 1 to -3.
Yes.
So the first element of the convolution must be -3 times 1, right?
That's okay. Like because it depends on where you take the seal. Say if I take the seal here, then will be like exactly flip that way. Because I um for whatever like classic signal processing, you
Uh-huh.
are applying to time, right? The access is time. So therefore, like people are very careful with this kind of causality. So okay, again, like for you guys, I don't actually know what I'm talking about. Don't worry about that. Um, so I mean, in the sense that you only want to apply the filter that like only for signals that you see before, right? So therefore, like you always start with zero here, right? Because like everything like the everything on this side, on the negative side, you actually don't see the signal yet. You are trying to filter the signal ahead. What's the example here is like when we are doing here, actually that's exactly what we're always doing is like we say like we apply this filter on this value here. I'm actually looking ahead. You see, I'm when I compute this filter here, I need to look at the samples like ahead of time. If you think of this as is time, and this is not allowed in many cases, right? Because for example, if I'm doing prediction like for stock, I can only like I can only know up to now. So therefore, like in practice, your filter is always like take actually uh you apply the the seal is here. If I seal is here, when I flip that, then I will have like as you said, I will have one minus seal one minus one. I will have this one as at this point here as well. I'm not sure. I can't
So
completely.
usually when we use the programming language like MATLAB,
Yeah.
I want to calculate the convolution between 1 to -3 and 1 to 4, then the resultant, the vector, the size is much greater than 4 and 3 because
Sorry,
the
just wait a second. Let
convolution.
me just quickly answer that. Convolution, yeah, convolution flips the filter and convolution does not. Yes. So sorry, can you repeat again? Like,
I mean, the standard definition of convolution is to enlarge the original system. But I think in the filtering is looks opposite.
no. Actually, that's one thing I said. Like, there's a caveat. Typically, people refer filtering as
Mhm,
convolution. There's
mhm,
always there's a flip of filter, but I don't
mhm,
want to add additional complexity for our discussion earlier on.
mhm,
So therefore, like I first introduced correlation, I'm calling filter, but I'm not in terms of signal processing people. Like I'm kind of like violating their very major important whatever belief, but in computer vision, it doesn't matter too much because you look at the open CV. By
mhm,
the way, the open CV function, the filter 2D, it
mhm.
it did implement correlation instead of like convolution. So I
I
guess
see.
I'm not totally what's that word? I don't know. So yeah. Uh so but like it's still like it's better to know that like for majority of people like in signal processing and whatever, when they say filtering, they are actually referring to convolution. Uh, but you for the rest of you don't need to worry too much about like this kind of like you just need to know that convolution is actually just a flip of your filter before you apply correlation. Yeah. So and my guess is what I want to answer still. I mean, yeah, I will have a little bit more. Maybe we will can kind of clarify you a little bit better. So, but let me yeah, let me continue first. Like I say, let me continue first. Hopefully, so I just give a very simple reason why people care about convolution. Actually, convolution is more natural in real world. For example, like if I'm playing a drum here, like and then like you consider I hit the drum like at 0.5 second, 1 second, and 1.5 second. Now I have this HT here is an impulse response. Impulse response will be like after I hit the drum, like how the drum will kind of like decay, like still have like some kind of like signal coming out from 0 second like, up to 2 second and continue probably like decay slowly. Now if I hit the drum like that, like 0.5 second, 1 second, 1.5 second, what do I expect the outcome will be? The outcome will not be correlation, it will be convolution. The outcome will be like H AT convolve if HT. Usually convolve they use the symbol like this star things. So my outcome is actually will be exactly like this. It won't be correlation because if you think of that, maybe I just hit it one time, like forget this two here. I just hit one time here. So I would expect like the decay will be like this way. I will have a signal like output like this way. So therefore, like I would expect like for example, let me redraw it here. Let's say I only have hit one hit here. Now I expect there will be some signal response here, right? I will have something here. Maybe this is a 1 second. I will add like uh, maybe this is a oops. Let me go down a little bit. Maybe this is a 0.5. Let's say here is 1 second here. Now, if I do correlation, what do I get? I'm basically doing correlation. Is like I take this whole thing as a signal, right? This is a signal, and then I correlate. Is I have a filter like this, right? So I will be like having this thing kind of like do a dot product with this guy here, right? So and then like you see like for the original signal here, for the region here is all zeros, right? So that therefore like this will be all gone. So therefore like I have this multiplied by this guy will be just zero. So that would be nothing, right? That would be, but I expect to have some signal, right? So instead like I should have this impulse response signal, sorry, not impulse, this impulse multiplied by the flip of this filter or flip of this impulse response like this guy here. So then in this case, when I do a dot product of these two here, I will get something, right? I get something here. That's precisely, uh, therefore, like you see, like that's why I will have the outcome. I will get something like this. So okay, I don't know whether I make it clear. So maybe it's not clear, but then you just take my word that like doing, yeah, I guess because I use already more time than I expected. So you can rewatch this if you don't get it, or like you just take my words. Basically, like convolution is exactly what's needed, like in this case. So if I have impulse response like this, and I hit the drum like this, the signal is the convolution, it's not the correlation. So therefore, like people like to consider convolution and study convolution first. Uh, and also, like as I mentioned, like because it's actually the convolution that satisfy the main theorem of like signaling system. Basically, like if you have like a linear and shift invariant system, that then this system can be represented uh, as a filter, like whatever signal coming in can be represented as uh, a what was the symbol I used for um, maybe call it G this time. So can be represented as a convolution of that filter with that signal. So I have like G convolve with F, something like. So, but this is like convolution, not correlation. No, don't worry about that. Yeah, but this is a general because this is also like partially like what's that called like uh graduate class, right? So therefore like and also like this is like kind of knowledge, like people expect you to know. Like for example, when you read paper, they won't explain like what is like correlation, what is convolution, what is shift environment, what is linear, because they expect you guys already know this kind of stuff. So therefore don't it's good to know. Yeah, basically. Um um And I guess, okay, I will go to the slides now. And I guess I can like very quickly flip through the slides. As I explained most of the stuff actually. So this is shift and variant. I already mentioned that. And then like linear system. I guess I will skip some of this now. So for thresholding, like note that like this is an example that it's not linear. If you have, let's say, take an image, do a thresholding, like if you set something is larger than something, is set it to 255, let's say. If you do a threshold, you get an image like this, right? This is one of the example. Oh, okay, I need to, again, that's one thing is I need to, oops. Okay, that's fine. Maybe that's example that like this kind of system is non-linear, but it's shift invariant. Yeah. So as I mentioned, like correlation, this is like what we explained so far is actually correlation. So I lying a little bit, I call it filter, but it's not lying completely because open series people also call it filter. So I'm not the only kind of like outlaw here. Convolution will be just flip the filter. So the precise math, like as you can see, like the original will be like this way. If I flip the filter, it will just become minus sign. So I won't go into the math here, but then actually you can show that like, yeah, actually this is like, we already say that, right? So this is just showing that why convolution is actually just flip the filter. It's like flip the filter, do a correlation. Okay, by the way, usually this is like usually the notation people may use. It's like your correlation is like this, convolution like this. This I already go through that. So also why math people like this way, as I mentioned, like if you any system like linear and shift invariant, you can model with a convolution or with some filter. Also like convolution have lots of nice property. I won't go through that now. So because but maybe I just go into the final slides. Yeah. This also I mentioned that already. Like so, if you have edges, you can do padding and so on. Yeah, this is a slide I want to slow down a little bit. So you see, like convolution have all the nice property, algebraic property you can imagine. So for example, it's associative. You have like A, B, A convolve with B, and then convolve with C. You can first do A convolve B. It's the same as you first do B convolve C and then A. So, but this is not true for correlation. And also like convolution is like, if you ignore the boundary condition, or if you ignore the boundary, actually the order is not important. Like you do A and then B, I mean A convolve with B is the same as B convolve with A, but correlation is not. Yeah. And you all have also this distributive law and like is linear, both of them linear. Convolution is really usually referred as filtering. And actually correlation is really matching, right? You see like which one is like, if you think of like the filter itself is a patch you want to look for, then like correlation exactly look for where is the patch, right? And sometimes the filter is also along a kernel, like you see like some people call this kind of filter kernel. So okay, I guess I'm going really pretty fast for here, so maybe just want to pause a second and see if you guys have any. Yeah. So, but I guess I typically when someone asks like, if you have any questions, that is typically no. But still, do you have any question? You're really great at asking questions. Kanjun. Yeah.
Yeah, Dr. Zhang, I have a question, but
Yes.
it's about the homework.
It's okay. It's okay. Like maybe I will stop here. You ask the question. I will just continue next time. Yeah. Yes.
So can I ask a
Yeah.
question?
Yeah. I guess you can ask
Yeah.
the
So
question.
actually, I tried the code you posted on the Canvas.
Yes.
So it worked. So it just captured the video.
Yes.
But the problem is, how can I turn off this video? So I just click the Q,
Oh,
then
you need.
video stops, but I cannot get back to the original the screen.
Oh, yes. Okay.
You just stop there.
It's frozen. That I guess you let me to oh, let's see. I probably have some.
So I think I have to stop the Python in
No,
order
no, you
to
don't need
get.
to. I think like you let me just take an example here. Let's see if I can. You want to make sure there's a destroy window. Oh, okay. Let me maybe here get to the end.
So I'm using Mac. Is it does it matter?
No. I think Mac will work fine as well. So let's say this one. I don't know whether that's this is like taking two pictures or something like that, maybe. Yeah, let's see if it's running. Yeah, it's running. Okay, so this one like this. So make sure you have this one. Like first time I forgot to have like destroy all windows, I guess.
So I have one,
You
but
have
the
destroy all
problem
windows?
is the code in your canvas
Yeah.
used full screen.
Oh yeah, that's a full screen. This okay, like that's a full screen here.
Oh, okay, yes.
You can set this off, then it doesn't have full screen.
Uh-huh.
And you can I think it shouldn't stop. Yeah. Maybe you set off the full screen and see like does it help or something?
Oh, okay, I see.
Yeah.
So then maybe I can just stop the windows and get back to the
Yes.
the original screen.
Okay.
I see.
So yeah, let's
Is
see.
there anything I have to do?
Let me get back the chat. Yeah. So and yeah, okay. So I guess I'm already over time. So just remember that like you guys also should submit your, I forgot like the same day, I guess is at the project proposal or something like that. So I can't forget the schedule. Like some of you may help me. Like I can take it up
So
also.
February 20 is the due for the first homework?
Yes. And let me quickly see the dates here. So yeah, also like you're supposed to submit the, oh yeah, 27 is the proposal, that's fine. And then like I'm also for the graduate students, I guess you should submit a presentation abstract as well. It should be quite simple. It's just pick a topic that you'd like to talk about, like give a title and so on. And let's see if I have anything like yeah, I guess that's it. I'm totally over time. So I guess I will just stop now. So and in case you guys have any questions or anyway, I will just let this open for like a couple minutes. So if not, I will see you guys next week then. Yeah, okay. Thank you. See you guys.
Thank you.
Yeah. Bye now.